Continuing our study of integration using partial fractions, we're going to look at the case where we have repeated linear factors. So what that means is that in the factorization of the bottom, q of x, we have a term of the form ax plus b to the n instead of just ax plus b. And in that case, the corresponding part of the decomposition into partial fractions is going to be, instead of having just a constant over ax plus b, we're going to have such a term, but that another constant over ax plus b squared, and then another one over ax plus b cubed, and so on until we reach ax plus b to the n. So if I have a zero of multiplicity, say 5, at the bottom, to it is going to correspond a sum of 5 different partial fractions, one for each power of ax plus b, from 1 to 5. So let's look at an example. Let's say we want to integrate x squared divided by x plus 1 cubed. So here the bottom is already factored for us, and there's only one repeated linear factor. Right? So we have a 0, which is -1 of multiplicity 3. And we don't have to do long division to start with, because the top is of degree 2 and the bottom is of degree 3. So that means we can start directly with the form of the decomposition into partial fractions, which would be in this case a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 cubed. One term for each power of x plus 1 from 1 to 3. And now we want to find the coefficients a, b, c. And to find it, we can, as usual, use the system method that we've seen before. It normally works, whatever case we're in. Or we're going to use something that is not quite the n-cover method, but something alike the n-cover method plus derivatives. We'll see what that means. In both cases, we're going to start the same way by rewriting the right-hand side as one fraction whose denominator is a common denominator x plus 1 cubed. And to do that, I'm going to have to write a over x plus 1 as a fraction with denominator x plus 1 cubed, which means I'm going to multiply the top by x plus 1 squared. B over x plus 1 squared is going to be rewritten as b times x plus 1 over x plus 1 cubed. And then c over x plus 1 cubed can stay as it is. So we obtain this new way of writing the same function. And now we have on the left-hand side and on the right-hand side two rational functions with the same denominator, so they must have the same numerator. In other words, x squared is equal to a times x plus 1 squared plus bx plus 1 plus c. Now if we're going to use the system method, we use the idea that on both sides of this equation we have a polynomial function, in this case both of degree 2, and two polynomial functions are equal if and only if they have the same coefficients for the monomes of same order. So that means we're going to rewrite the right-hand side in standard form, that is x squared times a constant plus x times a constant plus a constant term. In this case, the only term in x squared is a times x squared. For x, when we multiply through x plus 1 squared, we get x squared plus 2x plus 1, so we have 2a times x, and we also have bx, so we have x multiplied by 2a plus b. As for the constant, we have a times 1, we have b times 1, and we have c, so we have a plus b plus c. This polynomial should be equal to x squared. That means that the coefficients corresponding to the same degree must be equal. In other words, a must be 1 because this is the coefficient of x squared, and the other two coefficients, 2a plus b and a plus b plus c, must be 0 because they are 0 on the left-hand side. Now this is easy to solve because then if a is 1 and b is negative 2a, that means b is negative 2, and c is negative a minus b, and we found the values of a and b, so we plug them in, and we get c is negative 1 plus 2, so 1. What that means is that we can replace our function by 1 over x plus 1 minus 2 over x plus 1 squared plus 1 over x plus 1 cubed, so we can rewrite our integral as we have on the first line of this slide. Now to calculate these integrals, we know what to do with the first one. We get a log of x plus 1, and then we have two other terms. And I want to point out that if you think about it, this is just powers of the variables. Almost of the variable. You do a simple change of variable where u is x plus 1, then du and dx are the same. And what we have here is simply integrals of powers of the variable, of u to the negative 1 in the first case, u to the negative 2 in the second, u to the negative 3 in the third. So we can use, well, in the first case, we cannot use the power rule because this is a case where the power is negative 1, but we get a log. And in the other two cases, we use the power rule. When I integrate u to the negative 2, it's something of the form u to the n, so I get u to the n plus 1 over n plus 1. Well, n is negative 2. That means n plus 1 in this case is negative 2 plus 1, negative 1. So I get u to the negative 1 over negative 1, multiplied by negative 2, I get plus 2u to the negative 1. And similarly, u to the negative 3 as an antiderivative, u to the negative 3 plus 1, which is u to the negative 2, over negative 2. And of course, u was x plus 1, so we obtain as an antiderivative of x squared over x plus 1 cubed, natural log of absolute value of x plus 1, plus 2 over x plus 1, minus 1 over 2 x plus 1 squared, all this up to a constant. Now going back to the situation we had when we were looking for the coefficients ABC, we rewrote the right-hand side as one fraction, identified the numerator to get x squared equal a times x plus 1 squared plus b x plus 1 plus c. And then at that point where we were using the system method, I just rewrote the right-hand side in standard form for a polynomial and identified the coefficients of some order. An alternative to that is to observe that when you have this equality, you have it identically for all x, and certain values of x are more useful than others. For instance, I can, using this, what I refer to as n-cover method plus derivatives, we can plug x equal negative 1 in this. So that corresponds to the n-cover method in the sense that you use the value of x that nullifies important factors and therefore are going to get rid of certain terms in your sum. So if x is negative 1, the first two terms in my sum of three terms on the right hand side are 0, and I get only c on the right hand side. On the left hand side I get the value of x squared at negative 1, which is 1, so c is 1. Now that only gives me c, so to get a and b there is this trick of differentiating. If I differentiate this expression, I get 2x on the left hand side, I get a times the derivative of x plus 1 squared, so in other words 2a x plus 1, plus b times the derivative of x plus 1, in other words just b, plus derivative of c, which is 0. And now I can plug again x equal negative 1 to get my first term to be 0. On the left hand side I have 2 times negative 1 is negative 2, on the right hand side only b remains, so b is negative 2. And I can iterate this process. If I differentiate, I get 2 on the left hand side and just 2a on the right hand side, so a is 1. So that's a relatively quick alternative to the system method. Now let's take a look at another example. We want to integrate x to the fourth minus 2x squared plus 4x plus 1 divided by x cubed minus x squared minus x plus 1. Here you see that the degree at the top is not less than the degree at the bottom, and therefore the first thing to do is long division. We've discussed in the first video in this module how to do long division, and so here I'm not going to go through a step-by-step description of this long division. Here is what we would obtain with the different steps that you can verify. It's a good exercise for you to do it by hand. But you see that we would find a quotient of x plus 1 and a remainder of 4x, which means that I can rewrite the function I integrate as x plus 1 plus 4x divided by x cubed minus x squared minus x plus 1. So now the integral reduces to integrating 4x over x cubed minus x squared minus x plus 1, where the degree at the top is less than the degree at the bottom. The next step, of course, is to factor the bottom. You can readily see that x equal 1 is a 0 of the denominator, which means that I can factor out x minus 1. When you do that, you see that the second factor has to be x squared minus 1. And x squared minus 1 factors further as x minus 1, x plus 1. Therefore, we end up with the factored form x minus 1 squared times x plus 1. So here we have one factor that is a linear factor that is not repeated and another one that is repeated twice. So according to what we have seen, x minus 1 squared contributes in the decomposition into partial fractions two terms, a over x minus 1 and b over x minus 1 squared. On the other hand, x plus 1, which is non-repeated, contributes just one term, which is c over x plus 1. And we have to find the constants a, b, c. And to do that, we're going to again rewrite all this as one fraction with denominator x minus 1 squared x plus 1. That means that the first partial fraction, a over x minus 1, if I want it with denominator x minus 1 squared x plus 1, I have to multiply the top by x minus 1 and by x plus 1. For the second one, I already have x minus 1 squared at the bottom, so I only have to multiply the top and the bottom by x plus 1. So I get b times x plus 1. For the last one, I have the term x plus 1 at the bottom, so I need to multiply top and bottom by x minus 1 squared. So here is what we obtain, and now we have fractions with the same denominators that are equal, so they need to have the same numerators. So we have 4x equal to this expression a x minus 1 times x plus 1 plus b x plus 1 plus c x minus 1 squared. I could use the system method, but I'm going to go to the alternative, something like n cover plus derivatives. But mainly the idea here is to use special values of x, and for the special values of x that we're going to plug in this equality, we pick the values that make some of the terms 0. So in particular, we can pick x equal 1, which is going to make the first term and last term in my sum of three terms on the right hand side 0. So when I plug x equal 1, on the left hand side I get just 4. On the right hand side I only have b times 1 plus 1, in other words 2b. So that means that b is 2. I can also plug x equal negative 1 in this, and I get negative 4 on the left hand side, and on the right hand side the first two terms are 0, and the last term is c times negative 2 squared, so in other words 4c. That means that c is negative 1. Now to get b, we're going to use this trick that we've seen in the previous case of differentiating both sides. If I do that, on the left hand side I get just 4. On the right hand side I have a multiplied by a product, so I can use the product rule. That's 1 times x plus 1 plus x minus 1 times 1. So I get a x plus 1 plus a x minus 1. Then derivative of b x plus 1 is just b, and of c x minus 1 squared is 2c x minus 1. In this I can plug x equal 1 because it's going to make two terms 0. Then I have 4 is equal to a times 1 plus 1, so 2a. The next term is 0, then b, and the last term is 0. But we've already found b to be 2, so we get that 4 is equal to 2a plus 2. In other words, 2a is equal to 2, or a is equal to 1. So that means that in my decomposition into partial fractions, I can replace a by 1, b by 2, and c by negative 1. So this is what we get. And now, when we integrate 4x over x cubed minus x squared minus x plus 1, we really integrate 1 over x minus 1 plus 2 over x minus 1 squared minus 1 over x plus 1. So for the integral, we get antiderivative of x plus 1, which is x squared over 2 plus x, and then antiderivative of 1 over x minus 1, which is natural log of absolute value of x minus 1. Then we have the antiderivative of 2x minus 1 squared. That's something of the form u to the negative 2. When we integrate, we get u to the negative 1 over negative 1. In other words, negative 1 over x minus 1. I have to multiply that by 2, so I get negative 2 over x minus 1. And then I have minus natural log of absolute value of x plus 1. All this up to a constant. Now turn to the next video to see what happens when we have irreducible quadratic factors.